Hi, in this chapter, we will discuss the brief concept for the inverse kinematics. This is pretty simple chapter. Recall what's the difference between the kinematics and kinetics. Kinematics only handles the position and its time derivative. It's a calculus, okay? So like a position times time derivative velocity and acceleration. So you don't consider the forces for when you're handling the kinematics. As opposed to that, the kinetics, which is also equivalent to dynamics, is all about force and motion relationship. F equals ma and torque equals I alpha, right? So for the inverse dynamics is the opposite for the forward dynamics. So forward dynamics is like F is given and you can figure that out what's going to be the resultant motion. Torques are given, what's going to be the resultant angular motion. Okay, the inverse dynamics is when you know the motion, the position, like a linear linear acceleration or the angular acceleration, you can figure out what's going to be the force and the torques that generates those. So inverse kinematics, we should first think about what's going to be the forward kinematics. So kinematics for the biomechanics especially, you can just think of it as a joint angles. Joint angle, joint angular velocity, and joint angular acceleration. And that will generate the motion at the end, such as the end of kinematic chain here is such as the fingertip or your head motion, head position, or your foot position, etc. So if you have a fingertip position x and y, you will have a joint angle that will generate the x and y. That's the kinematics. So for example, if you only have a single segment, it's a pretty simple one-on-one matching. Once your theta is defined, your x is defined, your theta is defined, your y is defined as well. Suppose you have two segments, two joints of your body will generate this fingertip position x and y. That means you have a theta 1 and theta 2 will generate such a motion. So you have more joint parameters than the end effector, right? So similar manner, when you're generating the force at the joint, generating the torques, those are actually generated by the muscle force, muscle contraction. So either the muscle force or the tendon force attached to the bone will generate the forces, and those moment multiplication will generate the torque. So your force relationship at the joints will be expressed like this. So as far as you know what's going to be the F1 and F2 or what's going to be the theta 1 and theta 2, you will figure that out. What's going to be the endpoint motion, end effector position, x and y, or the joint torques. However, suppose that we want to do it in inverse manner. So we want to know, I want to actually place my fingertip to such a specific x and y position. And what's gonna be the corresponding theta 1 and theta 2? Or I want to generate the specific joint torques at the finger, finger joint. What's gonna be the muscle force or tendon force at each connecting point? So that's basically gives you more than one, like a unique answer, because you have more parameters, more variables, right? So sometimes it will give you multiple solutions here. Maybe this one is also a solution here, right? Well, I know it's anatomically impossible to make that posture, but mathematically you will have multiple solutions. Or sometimes if you have more joints, you will have even infinite numbers of solutions to generate those end position. So that's the challenge for the inverse kinematics, and many of motion planning research like robotics or some posture analysis is handling this issue. And human's body is very, very redundant system, very large degree of freedoms. So there are many studies using optimization, optimize maybe like a torque torque magnitudes or some power magnitudes, or try to understand how human moves those redundant degree of freedom to make such a specific posture. That's a pretty simple concept. I'd like to introduce how Jacobian is used to handle the inverse kinematics problem. Jacobian, we actually defined it in the previous chapter, like a first order partial derivative. Like we defined this when we are handling how your position or the velocity x and y, x dot can be formulated as theta dot, right? So by using those Jacobian, we could handle the equations of motion in a simple algebraic form. So same for the similarly applied for the inverse kinematics. So here I have an end position, the end point position, x and y. It could be expressed by theta 1 and theta for the double segment system. So Jacobian is like has a two functions x and y. So first function, the first row, second function, the second row, I have two variables, theta 1 and theta 2, and its derivative will give me the 2 by 2 Jacobian matrix. This could be also used for defining the velocity as a simple algebraic matrix form. And if I add another segments, like a 3-segment system, I will have more variable, like a theta 1, theta 2, and theta 3. So my Jacobian has a 2 by 3 because I have only two functions, 2 rows, and 3 variables, so 3 columns, so 2 by 3 derivative, first derivative, which will have a 2 by 3 Jacobian matrix, which could be also used for formulating velocity in a matrix algebraic form. So note that Jacobian is not necessarily a square matrix, depending on how many variables, how many sub-functions you have. Okay, so I can use this Jacobian to mapping the joint torques and the fingertip forces. Okay, suppose that I like to actually push a desk or push something with the fingertip force F. What's gonna be the corresponding joint torques? And can I solve this using Jacobian? That's what I'm going to talk about. So suppose that you have a very, very small displacement at the end, the fingertip, and that will correspond some small angular deviation at your finger joint. And since this is supposed to be a static motion, your work will be conserved. So your work done by the torques will be same as work done by the force. So torque multiplied the delta theta is going to be same as force multiplied the delta x. And note that your Jacobian can be used for relating velocity and the angular acceleration, angular velocity, like x dot equals jx theta dot. You can just divide cancel eliminate delta t. That's what I can get is delta x in terms of Jacobian and delta theta. So if you plug that into here, okay, so what you can have is torque multiplied delta theta is force multiplied by delta theta with Jacobian. So if you also eliminate delta theta left and right, what you can have is only the torques multiplied by the force in Jacobian. If you transpose both sides, you will have force and torque relationship in terms of Jacobian transpose. So Jacobian is also used to relate the force and torque relationship. Also, the Jacobian can be used for relating linear per se stiffness and the rotational stiffness. Okay, suppose you are applying the torques at the joint, and then you can actually figure that out what's gonna be the rotational stiffness, rotational resistance for the torque for the displacement, and I'd like to know what's gonna be the equivalent linear stiffness at the fingertip. So from the previous relationship between the torque and force using the Jacobian, I can replace the torque as k delta theta. And also I know the delta theta and delta x relationship using the Jacobian. So if I plug that in, what I can have, and then also doing the inverse for Jacobian transpose left and right, I will have Jacobian transpose inverse K rotational matrix in Jacobian delta x. It's going to be K delta x. So if I eliminate this, what I can have is linear stiffness could be expressed by the rotational stiffness multiplied by the Jacobian left and right. So the Jacobian can be also realize the linear and the rotational stiffness. It's because your very first definition for the Jacobian is relating linear displacement and the rotational displacement, and this could be used to interpret other relationships about torques and forces, etc. Okay, so in this chapter, the very first chapter for the basics of dynamics, we reviewed how we can obtain the equations of motion. And we also learn how we can solve it using the MATLAB OD45. And inverse dynamics may be the most useful chapter for you to handle the human body dynamic, human biomechanics analysis. So how formulating how the joint force and torques could be obtained from the measured kinematics information. And finally, I briefly go through inverse kinematics, the issue that many of motion planning researchers are handling. Okay, that ends the chapter 1, and thank you for your attention.